Assalamu alaikum. Welcome to the course of Electric Machine 1, lecture number 10. Today we are going to study about the losses, mechanical losses, then electrical losses, and relationship between load and losses, and then at the end, inefficiency. So first of all, losses. Whenever a machine transforms energy from one form to another, there is always a certain losses. The losses take place in the machine itself, causing an increase in temperature and a reduction in efficiency. From the standpoint of losses, electric machine may be divided into two groups. Those that have revolving parts, there are motors, generator, etc. They have rotors that are rotating, and those that do not have a rotating parts like a transformer, reactor, etc. They are stationary, mean the primary and secondary winding of a transformer are stationary. So electrical and mechanical losses are produced in a rotating machine, while only electrical losses are produced in stationary machine. In this chapter we analyze the losses in DC machine, but the same losses are also found in most machines operating on AC. The study of power losses is important because it gives us a clue as to how they may be reduced. And also the losses is directly affect the efficiency of the machine, so if we reduce it we will increase the efficiency of the machine. So first of all, mechanical losses. Mechanical losses are due to the bearing fraction, brush fraction, and windage. The fractional losses depend upon the speed of the machine and the design of the bearing, brushes, commutator, and slip rings. Windage losses depend on the speed and design of the cooling fan and on the turbulence produced by the revolving part. Rotating machines are usually cooled by an internal fan mounted on a motor shaft. So in mechanical losses we have bearing fraction, brush fraction, and windage, and then they also depend upon the speed of the machine and design of the bearing, brushes, commutator, and slip ring, while windage losses depend upon the speed and design of the cooling fan. Now electrical losses. Electrical losses are composed of the following. They have the following subcategories. The first one is conductor I square R losses, sometimes called copper losses. The second one is brush losses, and the third one is iron losses. So electrical losses, the first one is conductor losses. The loss in a conductor depend upon its resistance and the square of the current, that is the I square R losses. It carries the resistance in turns depend upon the length, cross-sectional resistivity, and temperature of the conductor. In DC motor and generator, copper losses occur in the armature, the series field, the shunt field, the commutating poles, and the compensating windings. They all have copper losses because there are windings made of copper. These I square R losses shows up as heat, causing the conductor temperature to rise above the ambient temperature, and because of these losses the heat of the winding or increases. Second one is the brush losses. The I square R losses in the brush are negligible because the current density is only about 0.1 ampere per mm square, which is far less than that used in copper. However, the contact voltage drop between the brushes and commutator may be produce significant losses. The drop varies from 0.8 volt to 1.3 volt depending on the type of brushes, the applied pressure and the brush current. So the I square R losses in brushes are negligible because there is very less current density, but the voltage drop between brushes and commutator produce a significant loss, that is about 0.8 volt to 1.3 volt. The last one in the electrical losses is the iron losses. Iron losses are produced in the armature of a DC machine. They are due to the hysteresis and eddy current. Iron losses depend upon the magnetic flux density and the speed of rotation, the quality of the steel and the size of the armature. So we already studied what are these losses, that is hysteresis and eddy current losses, and it depends upon the magnetic flux density, the speed of the rotation, the quality of the steel and the size of the armature. Now the relationship between load and losses, what happens when the load increase or decrease. A DC motor running at no load develops no useful power. However, it must absorb some power from the line to continue to rotate. At no load, it requires some power. This no load power overcomes the friction, windage and iron losses and provide for the copper losses in the shunt field. The I square losses in armature, series field and commutating field are negligible because the no load current is seldom more than 5% of the nominal full load current. So at no load there is some power required for the machine to rotate, and this no load power consume in the fractional, windage and iron losses and provide some copper losses in the shunt field. And the I square R losses in armature, series field and commutating field are negligible because the no load current is very less as compared to the full load current. When the machine is loaded, the current increases in the armature circuit. Consequently, the I square R losses in the armature circuit will rise. So when we load the machine, the current increase, and as a result, I square R losses in the armature circuit will increase. Hence, with the increase in load or loaded machine have more I square R losses as compared to no load. On the other hand, the no load losses mentioned above, there are windage and fractional losses, etc., remain essentially constant as the load increases unless the speed of the machine changes substantially. It followed that the total losses increase with the load. So remember that when the machine is loaded, the I square R losses or copper losses increase and overall the total losses increase, but the no load losses almost remain constant. Next, they are converted into heat. The losses are converted into heat. The temperature of the machine rises progressively as the load increases, and with the increase in load, the heat increases because the losses increases. The temperature must not be exceeded the maximum allowable temperature of the insulation used in the machine. We need to keep the temperature in the range. So the insulation used in the machine will not be affected if the temperature remain in the range. A machine loaded beyond its nominal rating will usually overheat. The insulation deteriorate more rapidly, which inevitably shorten the service life of the machine. And the last one is the efficiency. We know that the efficiency of machine is the ratio of the useful output power to the input power, and the input power is equal to the useful power plus the losses. Thank you.